Good morning, everybody. I apologize for being late. Uh, Rush hour traffic was really rough in my house, right? But anyways, are you ready for an exciting morning of chemistry, Chem 1105, with me, your host, Dr. White? All right, first of all, I do have to admit, one of your colleagues found I made a major error in grading 9 points, but that's why I say check your test. That's very rare, but once in a while it happens. So make sure you check when I do go over it that I did it right. And I think I'm going to sneeze. Excuse me, that was a slow evolving. Oh no, I'm allergic to students. No, I'm not. But anyways, check your tests always to make sure I didn't make errors. All right, we got a real exciting morning for you. Thank you. I can always use blessings from my friend up above. Anyways, got an exciting morning, so let's get started. All right, thumbs up, people. Do you see? Somebody's got their mic on. And thank you for shutting it off. All right, everybody see acid bases on your screen? Thumbs up, people. Help, thank you. All right, let's go through some of these for the acid base problem set. You should know this stuff, practice it on your own, because test number 4 is next Monday, probably later today or tomorrow. I'll put up the points breakdown information about test number 4, but it will cover acids and bases and organic chemistry. All right, what's an acid per the Bronsted-Lowry theory of acids and bases? You should know it's a proton donor. You can also put H plus as a shorthand for proton. What is a base per the Bronsted-Lowry acids and base theory? And the answer is proton acceptor. I just had a question from one of your colleagues, and the question is that yes, you'll take 4 hourly exams, and for your grade, I will use the 3 of the 4 highest. Now, if you've done well, let me go to face-to-face. All right, listen up. If you've done well and you say, oh, I don't have to take test number 4, don't do that. Why? Because there's going to be material on the final from test number 4, and students who don't take test number 4 say, I don't need it, then they don't do good in that part on the final, and you should. And I just realized I forgot something. Give me 60 seconds. I'll be right back. I'm back. All right, sorry about that. Forgot to put this on. Usually I don't wear it in the house, but when I teach, I try and wear it. That's my college ring from undergrad. I didn't like the PhD ring they sold. I should have bought it anyways, but I still didn't like it. But anyways, take test number 4, because if you don't study for it now, you might not do well on the final. So that's but I use the 3 highest tests. That way, if you have a real bad day and don't do good on a test, it's not going to ruin your grade. Oh, I don't know if I told you, when I was an undergrad, where I went to Technical Institute, Illinois Institute of Technology, we had a midterm and a final for most classes. And the midterm was either worth 40 or 50% of your grade, and the final was either worth 50 or 60% of your grade. Midterms and final week were not fun time for Dr. White or anybody else. A lot of stress. All right, let me get back to this. All right, next, you should be able to identify, based on the empirical formula, key acids and bases. I've already given this to you. HCl, hydrochloric acid, it's an acid. NaOH, it's a base. Sodium chloride, and you should be able to know sodium chloride is not an acid, it's not a base, it's a salt. And H2SO4, sulfuric acid, acid, NH3, base, HNO3 acid. Now, this isn't true for all chemistry, but it's pretty true for this class. If the formula begins with an H, it's an acid. If the formula begins with an alkali metal, it's a base. I'll say that again. This is true for my class, but not in general. If the formula begins with an H, it's an acid. If it begins with an alkali metal, it probably is a base, except for salt is an exception, obviously. And ammonia, you should know. All right, let's talk about pH. For pH, the pH scale goes from 0 to 14, never less than 0, never more than 14. If we look at my beautiful diagram over here, right, but anyways, at 7, you're at neutral pH. Below 7, it's called acidic. And the lower you are, the more acidic that solution is. And above 7, we call that basic, and sometimes alkaline. But for this class, I'll use basic. And the closer to 14 you are, the more basic the solution is. Remember originally, the original definition, acidic? For an acidic solution, the original definition was hydronium ion, H3O plus, greater than hydroxide, OH minus. For a basic solution, hydroxide, OH minus, is greater than H3O plus. And for neutral, H3O plus hydronium ion concentration is equal to hydroxide. However, it's easier to use pH, which is why I'm glad someone invented it and why it's so widely used, because this is much easier to know. So remember, pH equal minus the log of the hydronium ion concentration. And you know something? Let me open up something that I should have. All right. Does everybody see important information on your screen? Help me out, thumbs up, people. Thank you, Ishmael. All right. Remember, if H3O is equal hydronium ion concentration equal 1.0 times 10 to the minus X, pH is X. And you should go and look through this before test number 4. Let's go back to the problem set. And therefore, if we look at number 4, if a solution has a hydronium ion concentration 1.0 times 10 to the minus third, what is the pH of the solution? And is it acidic, basic, or neutral? pH minus log hydronium, put the number in, X is 3, therefore the pH is 3, it's less than 7, it's acidic. And if we look at number 5, if a solution has a hydronium ion concentration 1.0 times 10 to the minus 7, what is the pH of the solution? And is it acidic, basic, or neutral? And pH minus log hydronium ion concentration. And you put in that number, X is 7, pH is 7, 7 neutral pH. And I've got other ones you can try on your own. Now, if the solution has a hydroxide concentration of 1.0 times 10 to the minus 3, what is the pH of the solution? And is it acidic, basic, or neutral? Uh-oh, pH is minus log of a hydronium ion concentration, and whoever was mean and nasty didn't give us that, gave us this thing. What do we do? Well, first of all, you look at important information and see Kw, no, I wish that were me, but that's the ionization constant of water equals hydronium ion concentration times hydroxide concentration equals 1, actually 1.0 times 10 to the minus 14. And you can use that to solve for hydronium ion concentration. And then once you get that, you can use the pH minus the log of the hydronium. So what you need are 2 steps. And the first step, you'd take the hydroxide and solve for hydronium. How do you do that? Hydronium hydroxide equal 1.0 times 10 to the minus 14th. I want to get rid of hydroxide, so I divide by it. Whatever I do from one side, I have to do the other. Anything divided by itself equals 1. 1 times hydronium ion concentration, hydronium ion concentration, it equals 1.0 times 10 to the minus 14th divided by hydroxide. I put that number in because we're given it. And then I get 1.0 times 10 to the minus 11 equal the hydronium. Am I done? No, you're trying to get pH. How do you get pH? You use step 2, hydronium to pH. pH minus the log hydronium, put that in, X is 11, pH is 11, it's above 7, therefore it's basic. Then I have other problems you can follow along on your own. Well, first of all, really, a commercial public service announcement, that sounds better, from me, Dr. White. And that is, you should be doing these on your own first, even if after I go through it, try some I didn't do. Because remember bicycle? If you watch the video of me riding a bicycle, actually doing the problems, it looks easy until you try it yourself. And the first time you're on a bicycle, you fall off. It's better for you to fall off on practice problems than fall off on the test. You don't want to do that. Remember, if you have problems or have questions, ask in class. Also, don't forget, Monday and Wednesday at 5, I have my office hour. Please come by, ask questions. That's why I'm there. And good news, since we're on Zoom, ooh, Zoom, that doesn't look cool. But anyways, since we're on Zoom, you don't have to drive to COD. All you got to do from the comfort of wherever is log in. All right, let's move on. Now, what happens to the numerical value of a pH of a beaker water at pH 7.0 if you add a few drops of concentrated NaOH solution? Well, first of all, you have to know sodium hydroxide, NaOH, is a base. And what happens when you add a base to the numerical value? Whoop, wrong thing. And remember, pH scale 0 to 14. If I add a base, it's going to become more basic. That means that numerical value of the pH will increase. What happens if you add H2SO4? You have to know that is sulfuric acid. It's an acid. You don't have to know the name, you just have to know it's an acid. And it causes the pH to go down. Remember, oops, wrong one again. Right one. When you add an acid, the solution becomes more acidic and the pH goes down, closer to 0. Now, let's look at number 11. What happens to the numerical value of a pH of a beaker, and I could have put equal to pH 7, if of a beaker of a buffer solution, if you add a few drops of a dilute acid? By definition, a buffer solution is a solution that does not change its pH if you add a small amount of acid or base. And a few drops of dilute means very little acid, therefore the pH stays the same. And same thing if you have a buffer solution and you add a few drops of a base, guess what? The pH stays the same. All right, let's look at number 12. If you have to add 1.35 times 10 to the third milliliters of a 1.53 capital M molarity, I hope you know by now, NaOH solution to neutralize 1.87 times 10 squared milliliters of a aqueous, which means it's water solution, HCl solution, what is the molarity of the HCl solution? First question is, what are you trying to find? And the answer is molarity of HCl. Remember, M, capital M means molarity. What are you given? You're given 1.35 times 10 to the third milliliters of a 1.53 molar NaOH solution. What are you also given? The volume you use to neutralize this amount of acid, 1.87 times 10 squared milliliters of HCl. When you see the term neutralize, at neutralization, I should have written down here on here, but I didn't. Let's go to important information. It's a titration. And at titrations, we're going to show you a lab later today in Beyond Lab Z, where you get to do this titration. At neutralization, moles of acid equal moles of base. And for this class, I've simplified it for you. Shh, don't tell anybody, I've been nice. Remember that. Moles of acid times molarity of acid equals moles of base milliliters of base times molarity of base, because at neutralization, moles of acid equal moles of base. Well, if I put in a number, remember NaOH is the base, milliliters is this number, molarity 1.53. If I go on the other side, milliliters of acid, hydrochloric acid, 1.87 squared times 10 squared. And then I'm trying to find the molarity of the HCl. Well, how do I solve this equation? I get molarity M, capital M, HCl, alone on one side. How do I do that? Well, I've got to get rid of this 1.87 times 10 squared. Well, divide by it. Anything divided by itself in a multiplication like this will be 1. Whatever I do to one side, I'll do to the other. I've rewritten it. Molarity equals this right here. Notice 3 significant, 3, 3. And the answer is 11.0 is the molarity. Oh, let's do one more. These are fun. If you have to add 535, let's try that again. 358 milliliters of a 5.67 molar HNO3 nitric acid solution to neutralize 358 milliliters of an aqueous KOH, potassium hydroxide base solution. What's the molarity of potassium hydroxide KOH solution? We're trying to find molarity of KOH. It's a base. We're given how many milliliters. Then we're also given how many milliliters of the nitric acid is needed and the molarity to neutralize. This is a titration. As you saw, an important information, moles of acid equal moles of base. Milliliters of acid times moles of molarity of acid is the moles of base. Milliliters of base times molarity is moles of base. And put the numbers in. We want to solve for KOH, molarity, KOH. Therefore, how do I get rid of the 358? I divide by it. Whatever I divide by one side, I have to divide by the other. This cancels out. I'm left with molarity of KOH equals this, 333, and that's the answer. This one, you didn't even have to pick up your calculator. And that's the acid-base problem set. Probably this is one of the 2 or 3 most important areas I will teach you, if not the most important, for your own personal daily life and maybe also your professional life. Are there any questions? Going once, going twice. Oh, I'm not selling anything. I used to go to auctions with my brother-in-law. It was always exciting. At that time, he owned a bindery company and folding company. His company, you know how you get sometimes in medicine or other things, they fold up like 1,000 times the instructions and other things, and it's a big piece of paper, but it's folded, so it's like this. His company did that. And when certain companies would go out of business, they'd have an auction, and I'd go with him. The first time I went, and he said, keep your hands in your pocket and don't say anything. Otherwise, you just bought something for $50,000 or more. And he bought some stuff for his company, but it was always exciting. All right, no questions? What we're going to do today is I'm going to go through for a while some of the organic chapter, and then we'll do the lab, and then I'll let you go. Not yet, though. Look out, I'm in rare form this morning. Must be the good tea. and the company. All right. Now, I was talking yesterday about organic molecules. How do you draw them? Remember, there's always four, ooh, it's broken again, four bonds to carbon. Four, four, four. You can't see it as well. Remember that. And therefore, how do you know how many? If it doesn't have four bonds to it, then you add hydrogens. And yesterday I showed you propane. Molecules have names. I'll mention it in a second. And if we look at this carbon right here, there's one bond to it, but there should be four. So now you have to do high level math. 4 minus 1 equals 3. And that tells you this should have 3 hydrogens. If we look at this carbon, how many bonds do we have to it? 1, 2. But carbon should always have 4 bonds to it, but that one already has 2. So 4 minus 2 is 2. So there are 2 hydrogens. And I'll let you figure out the last one. I'll give you 10 seconds. Go. How many hydrogens should be there? Time's up. There's 1 bond to it. Carbon always has 4. 4 minus 1 equal 3. And that's propane. CH3, CH2, CH3. And that's the stuff, the chemical, you bet you didn't think of it as chemical, the substance that's in those white tanks that you buy for your barbecue. And it burns and gives off heat, and that's how you cook your food. Now, since I want to share the fun, I haven't yet. All right, 3 points each. Time for you to have some fun. Put in the hydrogen atoms for the following molecule. Your turn. Get to work. That wasn't polite, but get to work. Remember, there's always 4 bonds to carbon. Yes, 4. 1, 2, 3, 4. I should get some game show music so I could turn on and go da 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 da. Nah. All right, I'll give you another 15 seconds. All right, time's up. How do we put in the hydrogens? There's always 4 bonds to carbon. That's a better, huh? And now if we look at this, let's start. This carbon has 1 bond. 4 minus 1 is 3. Same thing here, 1 bond, 4 minus 1. Same thing here. Now let's look at this one. How many bonds does it have? Count the lines. 1, 2, 3, 4. 4 minus 4 is 0. I don't have to put any hydrogens there. Now, if we look at this carbon right here, it's got 1 bond to it. 4 minus 1 is 3. That's the most awful looking 3. That's better. Now let's look at this carbon. It has 1, 2, 3 bonds. There should be 4 bonds to carbon. 4 minus 3, 1 hydrogen. Let's look at this carbon. It has 1, 2 bonds to it. 4 bonds to carbon always. 4 minus 2 is 2. And finally, the last one has 1 bond, but by now, you know there are 4 bonds to carbon. 4 minus 1 is 3. And that's how you do it. And that's the skill, hint, hint, you should have. Now, this is called an acyclic compound. The prefix A means without. And sometimes I'll use an organic chemist. It's a branch straight chain compound because you have a long chain here, but branching. Now, that's acyclic. Organic chemistry has cyclic compounds, and sometimes we call these the cycloalkanes. They're represented by polygons. And the rule is each bend in a line is a carbon atom. Each end of the line, if you use it besides cycloalkanes or other cyclic, each intersection of a carbon of a line is a carbon. You never show hydrogens. Now, I should admit, Mother Nature and Dr. White love rings. In fact, a very complex ring was part of my PhD thesis research. Now, let's look at some rings. Now, if you have six carbons in a ring, this is the way most organic chemists will never draw it. See how much time it takes? This has got 6 carbons. And if you count it, 1, 2, 3, 4, 5, 6. And the way we draw it is this way. Ooh, Dr. White's having a good ring drawing day. Sometimes I don't. But notice I have every bend in the line is a carbon. So this carbon here is this carbon here. 1, 2, 3, 4, 5, 6. And this is called, you don't have to know, but I'll still tell you, cyclohexane. And notice this, I show hydrogens. On this, you don't. And this is an easier way to draw it. And let's go out somewhere interesting. All right, does everybody see on your screen cyclohexane in Wiki? Thumbs up, people, help me out. Oh, I think I saw someone help me out. All right, I'm assuming you can. And if you look over to the right, you see cyclohexane, and the first is the image using the line method. Now, they have other ways of drawing it, which I'm not going to cover. Now, one thing I should teach you will not be on the test. I think you're all familiar with Wikipedia. When it first came out, I used to call it Wikipedia. My students would talk, no, it's Wikipedia, Dr. White. They taught me the right way to say it. Now, for chemistry, especially organic chemistry, Wikipedia has been so heavily policed by organic chemists and other chemists, but most I can vouch for organic chemists, that for anything organic in Wikipedia, it's been a couple of years since I saw a major error. By the way, yes, I do have the credentials, and when I ask for a change in a Wikipedia, it's done. And I have, but it's been a couple of years. So if you're ever looking in Wikipedia for organic chemistry, guess what? It's going to be valid. Now, another ring is called cyclopentane. And I'll show you how to do this. Question is, in this ring, how many carbon atoms are in that ring? Will you count bends of the line? And 1, 2, 3, 4, 5. So the answer is 5 carbons. Here's one. You call that a square? Nope, organic chemists call that a ring. How many carbon atoms are in B? Your turn. I see somebody already has got the answer. I'll give you another 6.5 seconds. 6, 6.1, 6.2, 6.4. Time's up. And you count every bend in the line. 1, 2, 3, 4. And that's a 4-membered ring. Now, why are you learning this stuff? Well, in your hormones, there are 5 and 6-membered rings. Your steroids. In penicillin, there's a 4-membered ring. Now, let's do one more. Let's have some real fun. Again, how many carbon atoms are in this molecule? Your turn. Have fun. And it's the whole molecule, not just a ring. Oh, I gave it away. All right, time's up. Let's count how many carbon atoms are in this whole molecule. Well, for the ring, you count every bend in the line. 1, 2, 3, 4, 5, 6. So I have 6 in the ring. But here I have 1, 2, plus 2 more carbons. This is called an alkyl group, which I don't have time to teach you. So the answer is 8. We've got better try another one. All right, for D, again, how many carbon atoms are in that molecule? Boy, is that a pretty molecule. Now you know I'm an organic chemist. Time's up. Remember, every bend in a line in a ring is a carbon. 1, 2, 3, 4, 5. So the ring has 5 carbons. And by the way, I'm putting this down so you see how I'm getting it. You don't have to, but there are other carbons here. That's 1, 2, 3, 4, 5. And that means there's 10 carbons total in that molecule. Now it's time for Dr. White to let you meet an old friend of mine. You don't have to do it for this, but this is the ring system I did my PhD work on. It's called the bicyclo 222-octanone ring system. But say hello to my old friend. Now, one of the beauties of organic chemistry is when you have a certain functional group or type of molecule, if they're slightly different, when you have that functional group, they always react the same way, even though it looks different. You zero in on the functional group. Now, if you look right over here, can you see it right there? I have a door. I know what I can do with a door. I can go from this room to another. Now, if you looked at when you came to my front door, it looks different than that door. It does, but you would probably figure out what to do with it because you know in general what a door looks like or basic look of it and what you do with it. And if you were come to the chemistry or HSC building at COD, there's a front door that looks different than that door. And if you were going to classroom, it has a door that's different from the front door and different than that, but you know what to do. And that's what organic chemists use when we're doing reactions of molecules. Those similarities always interact the same way. And so we call that functional group chemistry. And the study of organic chemistry first is to know the basics, the functional group. Just like if you were a carpenter, you know how to use a hammer, you know how to use a nail, you know how to use pieces of wood to build things. Well, organic chemists use functional group chemistry to build things. And those things are molecules you use in your everyday. Or if we don't do it, one of the greatest of all organic chemists, Mother Nature, does it to build molecules you use in your daily life too. And with that, it's time for a 5-minute break. I'll see you at 9:50, and I'll be right back. Time to get going again. Now, I was talking about general reactions. And in organic chemistry, does everybody see combustion on your screen? Thank you. And what this tells us is when you have a saturated hydrocarbon, or it's called an alkane, and you react it with oxygen, you get carbon dioxide and water plus heat. Now, if I were to ask, give the products of the reaction of a saturated hydrocarbon with oxygen, you forget about the heat, even though it is probably the most important thing. So let's look at how you apply a general reaction like this to specific examples. And this is something you should know how to do. Let's start this one again. And on a test, if you were to see the following, give the products 3 or 4 points each. And the first one is this, what do? You look at this and say, well, this is only carbon and hydrogens. It's a hydrocarbon and it's a saturated hydrocarbon. And therefore, I'll abbreviate, saturated hydrocarbon plus oxygen gives CO2 plus water. We forget about the heat. Good news, organic chemists, unless you're figuring out charge weights like the 3-step problem we did in test 2, we don't balance equations. We're lazy. If we don't have to, we don't. Therefore, the answer to this problem is CO2 plus water. And if we look at B, what do you see? Only carbon-carbon single bonds. By the way, a double bond, you would see this between 2 carbons. A triple bond, you would see that. And we're not going to cover much of that except for double bonds in this class. I don't have the time. But this is a saturated hydrocarbon. And the general reaction is saturated hydrocarbon plus oxygen gives you CO2 plus water. And therefore, the answer here is CO2 plus water, if I can write it. And there you go. I'm going to let you try one. Now, when we're running out of room, organic chemists will bend the arrow. And I just did. So what would be the product or products for that reaction? Your turn. All right, time's up. If you look at this molecule, they're only carbon hydrogens, and they're all carbon-carbon single bonds. That's a saturated hydrocarbon. I'm reacting with oxygen, and this is something you need to memorize. Saturated hydrocarbon plus oxygen. What does it give us? Carbon dioxide, CO2, plus water. Therefore, this one will give you CO2 plus water. And this is octane, a major component of gasoline. Now, how many of you have ever been to winter and you look at the car in front of you, it's real cold outside, and you say, oh no, there's gasoline, a liquid coming out of the tailpipe. Is the car going to explode? Is it leaking gasoline so it can catch fire? And the answer is no. Because it's real cold, when a car starts out like that, the tailpipe and muffler are very cold. And in your engine, when you burn gasoline, combustion, that's what makes your car run, you make CO2 and water. Well, it's so cold that normally when that's hot, you don't see the water because it says a gas, a vapor. But now, because it's so cold, it becomes a liquid. And the liquid coming out of the tailpipe is water. Now, let me show you the chemistry instructor's favorite trick on an organic chemistry test. And that's putting a big, scary molecule and saying, what's the product or product? And if you don't know what you're looking for, yes, that's a big, scary molecule. But if you look at it, it's just carbon, hydrogens, and carbon-carbon single bonds. With that, I'll let you try it, and then I'll do it. Time's up. What do we have? Carbon, hydrogen, hydrocarbon, carbon-carbon single bonds, and this is a saturated hydrocarbon. What am I reacting with? Oxygen. What do I get? Carbon dioxide plus water. Therefore, I'm going to get carbon dioxide plus water. And that's the beauty of functional group organic chemistry and applying that to reactions. Similar types of molecules give the similar type of products. Now, another reaction I want to teach you, and you don't have to know the names, is called hydrogenation. And that's the addition of hydrogen gas, H2, to an alkene. An alkene is a double bond. And you need a catalyst which makes it go quicker, such as platinum, palladium, or nickel. And here's a general reaction, by the way. In organic chemistry, we use the term letter R, like math uses X, Y, and Z. That's 1 carbon, 5 carbons, 1,000 carbons. And another way of doing this reaction is whenever you see a double bond and you react it with hydrogen and a catalyst, you break one of the bonds. I'll never ask this on a test, but one of these is called a pi bond, one sigma. Sigma bonds I can break like that. I mean, pi bonds I can break like that. and sigma you don't. And you break the pi bond, and each carbon of the double bond gets a hydrogen. And you should know this reaction. And let's look how it works. When I put S in a bracket, that means product or products. Now, one thing I should mention here before we do this is most of the time I have been doing this. A plus B makes C, but organic chemists are lazy and sometimes we'll do the following. Write it clear first. Put reactants both at the base of the arrow and top and sometimes at the bottom of the arrow, like I have here. And this tells me this molecule reacts with hydrogen plus having a nickel catalyst. And what do we see that's different? When you look at a molecule, look for what's not a carbon-carbon single bond or carbon or hydrogen. That's where the fun is, a double bond. If I react it with hydrogen and a catalyst, and the catalyst can be nickel, platinum, or palladium. And you break the pi bond, each carbon gets a hydrogen. Now, this is important. Carbon-carbon single bonds are rarely broken except in the reaction we just did, combustion. Other than that, it almost never happens. Therefore, I start with 3 carbons here. I'm going to end up with 3 carbons. The only thing will change are the 2 carbons of the double bond, where I break the pi bond, each one gets a hydrogen. And now you can put in the rest of the hydrogens. There's 4 bonds to carbon. This should have 3, 1 hydrogen. So it's 1, 2, 3, 1 there, and 1, 2. 4 minus 2 is this. Now you can write it this way, which I would recommend, or you could also write it like this. And that's called hydrogenation. Now, in the real world, we use this reaction a lot for many things. Your instructor, me, I have worked at companies where we do hydrogenations of double bonds. And I personally have run supervised reactions of up to 40,000 pounds at one time. Which reminds me, and I'm going to put out an update. Special announcement. Ooh, I better make it special. Now you know it's a special announcement. Tomorrow in class, I will be doing something special. I will be taking you on a tour of a chemical plant. Most people will never see the inside of a chemical plant. And I'll show you some pictures tomorrow of a chemical plant I worked at. Now I'm going to cut it out of the video because I don't want that on the internet, but definitely show up. It's going to be exciting. Now, when I say 40,000 pounds, How many of you have ever seen the vehicle called a tank wagon that delivers gasoline to a gas station? You know, that long truck? How many of you have seen that? All right, we have a I don't want to touch my thumbs up button people day. I see one person. Well, thank you. A couple more. All right, you guys are jumping in. All right, let's do one thing quick or slowly. All right, I found one. All right, everybody see the picture? Well, maybe not. Let me do something. Everybody see the picture on your screen? In the right, it has a truck with that silver container behind it. Everybody see that? Oh, I forgot. We're not going to do thumbs up for Dr. White Tuesday. But anyways, this is called a tank wagon. Whether it's delivering milk somewhere, gasoline, or other chemicals or liquids like water. But anyways, they're standardized. They're 40,000 pounds, 5,000 gallons. And I've done reactions on a whole one of those of chemical that scale. Actually, I've done reactions I'll talk about tomorrow where we did a reaction often of 4 of those volume-wise or weight-wise. But anyways, I've done hydrogenations on 40,000 pounds. So you don't break carbon-carbon single bonds. Let's look at another example. And if we look at this, I'm going to do this. Now, this is totally different than the molecule I wrote before, but yes and no. Yes, it's a different molecule, but they have the same functional group. What's different? What's not a carbon-carbon single bond? What's not carbon or hydrogen? I'll give you 5 seconds to look at that. Go. Time's up. Right here. 2 lines between carbons, double bond. We're reacting with hydrogen. What's nickel? It's a catalyst. And the catalyst can be nickel, platinum, or palladium. And you break the pi bond, one of the double bonds, and each carbon gets a hydrogen. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across. 1, 2, 3, 4, 5 across. This is called the methyl group. That carbon is here. And which are my 2 carbons of the double bond? These 2. And notice I had 2 lines. I have 1 because I broke one of the bonds. And each one of those carbons gets a hydrogen. And you know how to fill in the rest of the hydrogens. 4 bonds to carbon. And that's how you do it. Oh, I'm going to let you have some fun. Your turn. What would be the product or products of the following reaction? 3 points each. All right, when you're done, give me a thumbs up. Oh, I forgot. Wait, today is, I don't want to do my thumbs up day for my class. So I better use a poll. Give you another 20 seconds starting now. Time's up. All right. How do we determine what's the product or product for this reaction? You look at the molecule you're starting and you look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. Oh, look. See, it even says it on the screen. Look, it's a double bond. What are we reacting it with? Hydrogen. And what's nickel? A catalyst. And the catalyst could be, in this case, it's nickel, platinum, or palladium. And you break one of the double bonds, and each carbon gets a hydrogen. Do you break carbon-carbon single bonds? No. So I start with 4 carbons. The way they are, I better end up with 4 carbons. My general reaction, which you should know, take the 2 carbons that are in the double bond, and to each one, add a hydrogen. So here are my 2 carbons, which are these 2 carbons. Notice I broke one of the double bonds. There's only one line. And now each one of those carbons, I'll give a hydrogen to. And then I know there are 4 bonds to carbon, so I can put in the rest of the hydrogens. And that's something you should know how to do. Now, I'm going to turn the switch off for this slide and maybe the next one too. In organic chemistry, it's in your daily life. All your fats and oils, like if you use vegetable oil or bacon after you cook, you know how you have bacon fat in your skillet? Those are organic molecules. Carbohydrates are, like if you eat starch or if you have sugar. The proteins, certain polymers, these are molecules that are very large that are used in our daily life. Let me show you one real quick. Everybody familiar with a water bottle? Well, the bottle here, this plastic, this is called a polymer. This is organic chemistry. Scary, isn't it? It's all around you. Your skin's organic chemistry. What's left in my hair? The water bottle. See the plastic around this stylus? That's organic chemistry. My mouse, notice I have a fancy mouse, the plastic shell and part of the wire, that's organic chemistry, not the metal part. It's all around us and even in us. Oh no, oh yes. And another example of organic chemistry, steroids, which you also know as your hormones. Now, switches off, fats and oils are called a triglyceride, and the functional group in fat and oil is called an ester, and there are three of them. I have time. And a number of years ago, I went to a new doctor. He had to retire. In the practice I go to, there's another one who's just as good I'm using. But I had my first annual checkup with him. And afterward, he called me up and said, "You better come in." I said, "What's wrong? I need to talk to you." And I don't know what it is. I think, but certain doctors, because I have a PhD or just who I am, they're pretty straightforward. And I like that. I don't like someone sugarcoating things. And he called me in. I went in, and he had a monitor in the examination room. They had an internet connection, a monitor, and computer. And he pulls up some stuff, and he shows me. And he also pulls up my blood work that they took. And he said, "Look at your triglycerides. See that number? You're in the 90 percentile. What does that mean? Well, you got a 90% chance if you don't change that, plus your high blood pressure, get it under control, you're going to be dead in 5 years." That woke me up real quick. I said, "No, I don't want that to happen. What do I need to do?" He says, "You've got to lower your triglycerides, the amount of fat and oil you take, like French fries have a lot, potato chips, mayonnaise, the good stuff in life," which I did. And that was more than 5 years ago. Good news, I'm still breathing and alive. And that's triglycerides. That's organic chemistry. Now, what's the difference? Switches off on this slide. What's the difference between a fat and an oil? A fat is a triglyceride that's a solid or semi-solid at room temperature, and oil is a liquid at room temperature. Fat's a solid or semi-solid. What's a semi-solid? Have you ever had butter sitting out for a while that you could stick a knife or your finger into and it's sort of squishy, but it's not really a liquid? That's a semi-solid. And an oil, you know what a liquid is. And the next time you happen to be at home or you go to the supermarket and you see vegetable oil, corn oil, or whatever, it's going to be a liquid unless they have the room it's in real cold, then it could solidify like 32 degrees Fahrenheit, and that's not going to happen. So fat, solid, semi-solid room temperature, oil, liquid at room temperature, triglycerides. Now, I've worked in this industry and switches off. There are different types of fats and oils. And the two main important ones used by the chemical industry are beef fat, which we call tallow, and pig's fat. There's two grades, yellow and white grease. And these chemicals, beef fat, tallow, pig's fat, yellow and white grease, are used to make many other chemicals we use in our daily life. Don't get grossed out because they're processed and made into other things, but they start with tallow, beef fat, or white grease, yellow grease, pig's fat. Now, I worked for a company. I was the laboratory manager for North America called Unichem Chemicals, which at that time was part of Unilever. And every week, we used, depending on how good our business was doing, 2 to 3 million pounds of tallow or white or yellow grease every week. That's a lot. Now, we sold to companies that made things like the bar soap you use. Yep, that comes from mainly beef fat. Don't get grossed out. It's not that bad. It's actually quite good. If you use a fabric softener, it comes from tallow, beef fat, or yellow grease, white grease. What's the difference? Well, because it's cheaper, if you can get white grease, yellow grease, pig's fat, you buy it. Because if it's only like 2 cents a pound cheaper, but if you're buying, oh, a couple 100 million pounds a year, that adds up real quick. Now, how important are those? That's cooking is cooking. I don't know if they still do or not. They might. I thought they were adding beef flavoring. Someone brought up McDonald's French fries. I haven't been to McDonald's in at least 20 years. I'm a hot dog person myself, not a hamburger person. But anyways, how important is tallow to making chemicals? Many contracts for the price of chemicals that are made from tallow are based on the price of tallow that week. Where can you find the price of tallow? Hang on. Once a week, if you know where to look, and I do, it's in the Wall Street Journal. It's that important. It's on the same area where they have the price of gold and other things. Also, there's a weekly magazine put out for chemists and people working in the chemical industry called the Chemical Marketing Report, CMR. That comes out weekly, and it also has the weekly price of tallow and other important chemicals. Now, everybody see at the bottom, I think you're all familiar with coconut oil, maybe not, soybean oil, vegetable oil or corn oil, olive oil, I think you're all familiar with. And there's an interesting oil that's used mainly for cooking. It's called rapeseed oil. How many of you have ever bought rapeseed oil in a supermarket in the United States? And the answer is, it's not there. Long ago, when they tried to sell rapeseed oil, which is an inexpensive cooking oil, which is used throughout the world, especially in countries that are economically stressed, poor countries, is cheaper than all the vegetable oils and other things. When they tried selling it in the United States, the American housewives said, rapeseed oil? I don't want to buy it. And a lot of the rapeseed oil is manufactured in Canada. And the association that makes that, someone there came up with an idea. Let's see, Americans won't buy rapeseed oil. We're in Canada, it's an oil. Why don't we call it canola oil? And that you can find in any supermarket. It's really everywhere else in the world. It's called rapeseed oil. Names make a difference, obviously, when you're buying things. Now, switches off. When you eat oil or fat and you chew it and it goes, or you swallow, gets in your stomach, there's acid. H plus is a general way of saying acid, and water, and you make what's called fatty acids and glycerin. And your body uses this to do various things your body does with that. Now, Dr. White's organic chemist, my knowledge of the human body with that is limited. Now, I hate to scare you, but your body is a walking organic chemistry plant. In your stomach, that reaction I just showed you is going on if you eat that and other things. And if I look at the clock, I think this is a good time to say it's time for our lab, and we'll continue organic chemistry tomorrow. You guys all ready for a good lab? Everybody say, yes, Dr. White. I heard that. All right, today's lab deals with titrations. Let me get to the top. And what you're going to do is do a titration of an unknown molarity hydrochloric acid solution. You'll be titrating this with sodium hydroxide. And a titration, as we did earlier, when you add a known amount of an acid or base of a known molarity to a known amount of an acid or base of an unknown molarity. And this allows you to calculate the unknown molarity value. And at neutralization, you use a pH indicator, which changes color. Today, we'll be using bromothymol blue. It goes from a yellow to blue when the pH crosses about 7. And the following is true. At neutralization, moles of acid equals moles of base. For this one, and it says monoprotic, only one proton, which for this class I've kept it simple. That's all we'll do. Milliliters of acid times molarity of acid equals milliliters of base times molarity. Now in this case, we're solving for this. So how do I solve for it? I get a loan on one side. So I divide each side by milliliters of HCl. This cancels out. And this is the equation you should be using. And what you'll do is find out what the milliliters of NaOH are needed to make the color change when adding it to the HCl. Now, this will be on the label, and I'm going to show you this in the Beyond Lab Z titration, and you'll be doing this. Now, notice I have the procedure. Let me open up Beyond Lab Z. All right, you should see Beyond Lab Z where it says welcome. Now it says need technical help. No, I don't. And where it says chemistry and where this is on higher ed, you click on open, which you've done before. Now, does everybody see welcome to virtual chem lab? Help me out, thumbs up, people. Thank you. Now, what you'll do is where it says acid-base chemistry underneath the worksheets, you'll click on that. And then where it says, scroll down, right here, acid-base titration of an unknown HCl solution. Does everybody see that? It's highlighted. Well, I'm going to assume you do. Let me check. Yep. Where it says acid and base titrations. Click on that. And now everybody, do you see the lab? Thank you. Now let me do this. First of all, I'm going to move over here some stuff around. Now over here, notice I have unknown sample 12. You need to write that down. On the sodium hydroxide bottle, the molarity is 0.2564. You need to write that down. Over here in the upper right, left, you have the burette. You know how to read one. We did it the last lab. It says 0.00. Now, notice in the beaker, it's already yellow. They have already put for you the bromocresol green. Goes from this yellow to blue. Now, I'm going to teach you some very high level, totally secret titration tricks that chemists who have done a lot of titration use. Now, it's not in the lab, but this will help you out. It's common sense, but common sense is not common. When you have an unknown like this, the first time in conductivity, I don't know what that's good for. This is the valve, you did it the last lab, and I'm going to open it up. Now, this is called shotgunning it in. This first time, I'm not going to record how many milliliters I used. I'm just looking to see how much approximately I have to add. And notice I was at 16.246, let's see. One, two, three, four. That's the one thing about there's 2, 4, 6. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So each one of those is a tenth of a milliliter. 1, 2, 3, 4, 5, about 16.55 because the bottom of the U is below that. Now that was, I know about where I have to do it. So now, and by the way, when you're at that, the pH shoots up because you're adding it, you're now neutralized all the acid, and you're just adding base. But go by colored, not by this. Now I'm going to exit this. And because they've got it set up, I'll click on it. And now I'm going to do my titration for real. I know at about 15 milliliters, I should slow down. Notice we have the same unknown, 12, same molarity. Now I'm going to write down those numbers on the lab, and I'll show you that in a second. Here I'm at 0.0. If you want to use this, you can put it over here. And now I'm going to add it, and watch what I'm going to do. And now I'm going to do it very slowly. And I'm going to look and watch. And I've stopped. And this one's a little more accurate, 16.2. You're going to have different unknown, so you have to try it. And you do this once. Now, you can come back and watch the video to see how I did this. Let's go back to the lab. In table 1, you'll put your unknown number. Now, they have already put in the beaker. In real life, you have to do it, but they've made it easier for you. 25 milliliters of the HCl. You have to write down the molarity that was on the bottle for NaOH. You write down the initial volume of the burette and the final, like 16.2, 0.0. The total amount of NaOH is B minus A. And then you use equation A, 3, milliliters of NaOH, the molarity is on the bottle, the milliliters here is 25, and that will give you the molarity of the HCl, which you put down here. Now, in real life, whenever you're doing a titration, you always do it in duplicate. You do twice. And here, I'm having you do the same thing. You'll put down your unknown number. It should be the same. The molarity should be the same. This, I don't know if it's exactly 0, where you end up, and you do these calculations. And notice I have how you do it. And then after you exit the lab, repeat steps 3 through 9. And that's our lab. Oh, one other thing, you know what I'm going to do. There's some questions for you to answer. I don't know about you, but I had a fun time doing that. I think you will too. So that's the lab. And if I look at the clock, this is a good time for me to say, I'm done. Gang gesund. Oh, the unknown number, Lily, is on the bottle. I'm going to go backward. Norp. I rewound the tape backwards. Oh, that was awful. Let me show you. That's a good question. All questions are. All right, Lily and everybody else, see on the bottle of the sodium hydroxide, it has the molarity, and this one is 0.2564. Underneath the HCl, it has unknown number 12. And now, do you know how to find it? And that's a good question, because I bet other people might have that same question, and now they know the answer too. And now I can do instant replay. I'm done. It's time for me to say, gang gesund. Bye now. I'll see you tomorrow, and we'll finish up organic chemistry.